Well, welcome back. This will be part two of our exam one review. This will be the second half of the exam, which will be problems 5, 6, 7, 8. So let me share my screen with you and we'll begin. So just a brief recap. There was the values that we had. As you can see, for 5 and 6, pretty much everybody did number 5, hands down, and did it pretty much exactly right. And it was a little split. You can see half and half on the second one. So let's begin with that. Let's look at 5 and 6, and let's see why 5 and 6, or what's the difference between the two. For me, I think 5 was more preferred by you guys because we had some problems very similar to this in class. So for me, there's not much difference between the two. Maybe 6 is a little more challenging, but 5 is pretty straightforward, and that's the one most people went with. So let's talk about that one first. So I found my reactions. There's my positive shear at A, positive shear at B, and I saw from my shear at A, got a positive value. I saw from my shear at A, got a negative value. So I know I'm going to start with a value of 2.8 and end with a value of negative 3.2. I just got to connect those dots. So you can see I have 1, 2, 3, 4, 5 different segments with really no load. And I know with no load, then the change in shear is 0. So starting off here at 28, there's no load, no change in shear, so I stay at 28. Now as I go from left to right, my shear is going to change equal to the applied load. In this case, 1 kip, and it's down, so it's negative. So I go from 2.8 to 1.8. Again, no load, no change. Then I hit 2 kips, minus 2 to 0.2, no change. Drop 1, 1.2, no change. Drop 2, 3.2, no change. So I connect the dots. So I got this nice stair-step effect of 5 different zones, each zone having a constant shear. Now I go to the moment equation. I know here at A, I have a pin, which I have no moment. Another pin here at B. I don't know if that's B. Yeah, B. Also no moment. So I'm going to start at 0 moment, end at 0 moment. Now remember what we're going to do here is the change in moment between the 2 points. I'm going to sneeze, and I'm going to do proper hygiene. I'm going to sneeze into my arm. Well, I thought I was going to sneeze. Maybe I'm not. When I do sneeze, I will try to sneeze into my arm or to my elbow. Okay, we know that over this region here, the change in moment between 2 points is the area of the shear diagram. Well, all these areas are going to be rectangles, and they're all going to be base times height. So in this case, base 4 times height, 2.8, that's a positive area, a positive change of 11.2. So 0 plus 11.2 is 11.2. And of course, the slope of the moment diagram is equal to the value of the shear, and the shear is constant, value of 2.8. So the slope here is 2.8. Now the change in moment from 4 to 8 feet is this area of the curve. Again, base is 4 feet, height is 1.8. Adding that to 11.2, I get 18.4. And that slope is smaller. It drops down to a value of 1.8. So again, constant slope, positive 1.8. Over the next region, I have a little small negative change. So all these bases on all these rectangles are 4 feet, and then the height. In this case, it would be 4 times 0.2. That's only a 0.8 change. So you can see it drops down 0.8, and a small negative slope given by this value here. And just repeat this. The area in this part of the curve drops us to 12.8. Area in this part of the curve is 12.8, drops us to 0. So there's my moment diagram. Now the questions that were asked were, what's the maximum moment, where does it occur? Well, I look at my diagram, it looks like it's 18.4 and occurs right there at x equal 8. What's the maximum shear and where does it occur? Well, maximum shear, remember, sine is direction, so the maximum value is 3.2. and it occurs at B. And then finally, what is the slope of the bending moment at x equal 5? Well, x equal 5 is just past 4 here. So what's this slope? Remember, well, the slope of the moment is the shear, and the shear is 1.8. So the slope would be 1.8 kilonewtons. And that's problem 5. Again, that's what everybody loved and worked. One or two of you worked problem 6. And really, at this point, it's a little more challenging problem. Starts off the same, though. I find my reactions at A and B. See, there they are. I know I have a starting shear value here of 0 and a starting moment. That's a negative bending moment. And on this end, no shear, and that's a positive bending moment. So I start my diagram out at 0 shear. I got to do my work, come back to 0 shear. So starting at 0 shear, the change in shear is the area of the load curve, which is 0, so no change. Start at 0, stay at 0. Then I hit AY. AY was 650, so my shear instantaneously changes to 650, from 0 plus 650. Then I have this distributed load, which has a value. Area under that curve would be base times height. That's 1200, so 650 minus 1200 brings me to negative 550. And then you see BY is 550 up. That brings me back to 0. And there's no change here because there's no load. So there's my shear diagram. I guess why this problem is a little more challenging than problem 5 is that we now have to find this point. We go from positive shear to negative shear. We need it just to be able to find the area of these curves to predict our moment. So remember, the change in moment or the change in shear force between these 2 points is 650 to 0. That's a change of 650. And the corresponding area under the curve would be base times height. There's my height and there's my base. So I can solve for x1 very easily. In this case, it's 3.25, which makes sense. This side's higher than this side. You'd expect it to be shifted to the right a little bit, or right of the center. The center is 3. So then I can just use my shear diagram to construct my moment diagram. So starting at the left edge, that's a negative 200 bending moment, so negative 200. And whatever happens, I need to end up at positive 100 on this side. So the change in moment is the area in the shear diagram. Well, it's 0, so there's no change in moment, so moment 0. Now the change in moment over the next distance, which is x1, 3.25, is this area. It's a triangle, 1/2 base, 3.25, times height, 650. I got 856.25 positive change. Well, I'm sorry, added to negative 250 gives you 856.25. The slope of this curve starts off at a large positive slope and decreases to 0. So there's my large positive slope getting all the way to 0 slope right at the top. Now with the remaining segment, the 2.75 feet, I'm going to drop this amount. This is a negative area, so 1/2 base, 2.75 times height minus 550. Subtracting that from 856.25 brings me down to 100. It starts off at 0 slope, and then the slope decreases to negative. So again, 0 slope decreasing to a negative slope. In the last 4 meters, there is no shear, so there is no change. So I hit at 100, I stay at 100, and that matches my 100 bending moment. So now answering the questions, what's the maximum bending moment? Where does it occur? In this case, there it is right there on the graph, 856.25 pound-feet happens right there at x1. So that would be 4 feet plus 3.25 or 7.25 feet. What's the maximum shear force? Well, let me look at my shear diagram. It looks like it's there, 650, really at A or just to the right of A, which is at 4 feet. And then what's the slope at x equal 4? Well, x equal 4 is right here. What is the slope of my moment diagram right there at x equal 4? Well, it should be the value of the shear. So just to the right, it's 650. Just to the left, it's 0. I put the 650 as the answer for that. So again, yeah, I guess looking back on it, I would say that question 5 was way easier than question 6, and I think you guys agreed. So let's do another quick review of the last 2 problems. Again, it was pretty evenly split. Results were pretty much the same, so really no clear indicator which one of these is the best. So let's look at those real quick. There's 7 and there's 8. They both have the same basic characteristic, is that they have a pin. 7 has a pin at B. This is also B. And because of the reactions, you're going to have to separate these two, this structure into 2 pieces to find all the reactions. And once you do that, you should be able to draw the shear moment diagram. So that's why I don't think there's a big advantage to either one of them. So we'll start with 7 first. So I have a little more work to do on all these problems. So I begin with taking a free body diagram of AB. There you can see it. So there's my positive shear at A, my positive shear at B, 10 kilonewton load. I can solve for that. So I went ahead and solved for my shear at A and B. And then I have the free body diagram from B to D. There it is. So this shares the same shear. So the shear at B is transferred. There's my reaction at C, and there would be the shear at D. So since I've solved for the shear at B, I can apply that there. I only have 2 unknowns. So I found the reaction and then the shear at D. So quite a bit of work just to get started. So now I can go back up and I can start with my shear at A, which was 6 kilonewtons there. And I know when I get to B, I better get -4. When I get to D, I better get 4. So I've got some target points. Plus I know my reaction at C, that this change in shear because of the reaction at C better be 38. So let's get started here. So I know I'm going to start at 6. I look at the load for the first 4 meters. There's no load, so there's no change in the shear. Then I encounter a point load of 10, which changes the shear by 10, brings me down to -4. Again, no load applied over the last 6 meters, so there's no change. That brings me to a shear of -4 kilonewtons at B, and that's great. That was one of my target values. Now, over this, from B to C, over this 5 meters, my shear diagram should change by the area under that part of the curve. So base of 5, height of 3, that's 15 kilonewtons. That's negative load, so it should drop. So -4 minus 15 is -19. And then just as I get to C, it jumps up 38. So -19 plus 38 gives me +19. Oh, phone's ringing. Not for me. We'll continue. The change over the last 5 meters is also the area of that part of the curve, which is again 5 meters times 3, that's -15. So 19 minus 15 is 4, and that gives me +4 shear at the end, which matches what I had computed. So I feel pretty good. It's a strange looking diagram, but that seems reasonable. So now on to the moment. So what do I know about moment? I know the moment at A, pin is 0. The moment at the hinge B should be 0. And the moment at D should be 0. So I got 3 target points. A is 0, B is 0, D is 0. So starting at 0, the change in moments, the area under this part of the curve, which is 6 times 4, which is 24. So it goes from 0 plus 24. The slope of this curve is given by the shear. The shear is constant positive, constant positive. Over the next 6 meters, I have a change of this rectangular area. That's 6 meters times 4. It's -24. So it drops me down to 0, which is great. That was one of my target values. I knew my hinge B should be 0. And the slope of that part of the curve should be given by the shear. And the shear is, again, constant negative. So it's a constant negative slope. That's pretty good. I'm halfway there. Now the next one is a trapezoidal shape. So the change from here to here is the area of this part of the trapezoidal curve. And I found that by averaging my two ends, the average of 19 and 4 over 5, that gives me a drop of 57.5. The shape starts off with a negative slope of 4 and gets steeper. So that's a slope of negative 4, and it gets steeper. Really, the slope right there would be minus 19. Then the last 5 meters, this is the area of the shear diagram. It's the same 57.5 as here, except it's positive, so that brings us back to 0. That's great because I know the moment at D should be 0. And what's the shape of the curve? Well, it starts off at a positive slope of 19 and gets smaller to 4. So these shapes are the same, they kind of just mirror images of each other. So that worked out pretty well. So then answer the questions at the bottom. Maximum moment, where does it occur? Well, there's the maximum moment, 57.5 kilonewton meters at point C. What's the maximum shear force? I look at my shear diagram. It looks like it's really at C, either positive or 19, positive or negative, it's still 19. And then it asks you, what is the bending moment at X equal 10 meters? The slope of the bending moment at 10 is right here. What's the slope right there at the bending moment? What's the shear, which is negative 4, and has units of kilonewtons. Okay, so we're almost done. Here's the last problem. Really conceptually about the same amount of work. So now I'm going to break it up into 2 free body diagrams, one from A to B, there you can see that one, and then one from B to C, and that's here. So at A to B, positive shear at A, positive shear at B. This is the concentrated equivalent of the uniform load, which is 2 times 10 or 20. And then there's, don't forget your concentrated load of 10 kilonewtons at 4 meters. So when you solve for that, you'll find the shear at A is a little bit bigger than the shear at B because of that shifted load. What I get for the shear at B, I can pass on to my free body diagram at BC, and that only leaves me the shear and moment at the fixed connection. So I found those. I found the moment to be negative and the shear also to be negative. I got lots of target values. So I know I'm going to start off the shear of 16. The shear at B should be negative 14. The shear at C should be negative 22. So I got this value, this value, and this value. See if I can make them work. Well, starting at 16, I'm going to have to include this point here where the force is. So the area of just this part of the loading curve, which is 2 kilonewtons per meter times 4, or negative 8 kilonewtons. So 16 minus 8 gives me to 8. And then as I pass under this load, my shear changes by that value, minus 10. So 8 minus 10 is minus 2. And then the change over the next 6 meters should be this part of the curve, which is the base of 6, height of 2, that's negative 12. Negative 2 times minus 12 is negative 14. That's great because that matches one of my values at B. And we can finish it by going over the last 4 meters. So the change in shear here should be this area under the load curve, which is 4 times 2, which is 8 minus 8. So negative 14 minus 8 is negative 22, and that matches the shear at C. That's pretty good. All's well there. So let's do the moment. What do we know about the moment? Well, the moment at A is 0. At the hinge is 0. But at the fixed connection, we know the moment. It is here, negative 72. So I have target values of 0 at A, 0 at B, and negative 72. So I just need to match that up. And my shear diagram will help me do it. I guess the challenge here is that all these shapes are trapezoids, a little bit more tedious area calculation. So I know the change in moment from 0 to this value is this area of the curve. And again, if you average those values, you'll get the average height over the times 4 will give you a value of 48. That's positive error. So 0 plus 48 gives me 48. The slope at the beginning is 8, and it drops to, 16. and it drops to 8. So this is not a flat slope here. This is still peaking. But then the slope changes dramatically from positive 8 to negative 2. And the drop from here to here is this part of the curve, which you can see if you average those two heights, you get 8. 8 times 6 is 48. Negative, positive 48 minus 48 gives me the 0. And that matches because I know I have a hinge there. And I can continue to match here. Should have the area under this part of the shear diagram, 14 and 22. If you average that, you should get 18 minus 4, and 18 minus 4, 70 is negative 72. So 0 minus 72 is negative 72, and that matches my moment. The shape, well, this slope is negative 14 here and increases. I know I didn't really draw it that way, but it really should increase. Obviously, this 72 is much larger than 48, so this diagram's not to scale. So I finished by answering the questions. What's the maximum moment? Well, the maximum moment's here, negative 72 kilonewton meters, and that happens at C, the fixed connection. What's the maximum shear force? Well, looking back at the shear diagram, oh, it looks like it's negative 22, also at C. And then what is the slope of the bending diagram at 5 meters? So I come over here and I look at 5 meters, which should be right about here. What's the bending moment there? It should be the shear there. Well, what's the shear? Well, it starts at 2, and see at 5 meters, that'd be 1 meter over. So it's dropping down. Well, remember the change in shear is in the load curve. The load curve is changing every foot by negative 2. So starts at negative 2, 1 then would be another negative 2, so negative 4. So the slope there is negative 4. Okay, so I hope that helped you some with the review of the first exam. And don't forget, when we get to the final, we'll talk about this some more, but this material will be back on the final in part 1 form. So if you have any questions about this or my evaluation, please email me. If that doesn't work, we can do a phone call. If that doesn't work, we can try a Zoom meeting. We'll see how that goes. So until then, or until next time, take care.